Okay, recording's in progress, so we'll share the screen. All right, so trust you had a good Thanksgiving weekend, and we're down to our last few weeks before we're all done. So we only have 2 weeks left on the calendar, this week, next week. We're already up to 11.10. We only have 2 sections left, 11.10 and 11.11. I did give you back your quiz. It seemed like a long time ago, but Wednesday we had a quiz. So I should have emailed you back your quiz, and I emailed, I sent the Canvas announcements to solutions video. So if you didn't get that, please let me know. Okay, so we have 11:10 and 11:11 left. Okay, we really can take our time with that. So that means we're going to probably end early every day from here on out. We'll get our last quiz this Friday. Okay, we are going to aim for Thursday the 9th for exam 5. We're just about done. So that means on the 10th, it'll just pretty much be an office hour. Okay, so you can come or not to join office hours. And then our final exam is on Friday the 17th, 8:10 to 10:40 a.m. Use the same Zoom link as we've always been doing. And you say, how do I study for the final exam? Just study the previous exams. Okay, just look over all the exams from the past. Okay, and you can have 5 formula sheets. The easiest thing, in my opinion, to do is just have your cheat sheet from the first test, second test, third test, fourth test, and fifth test, and just put them all together, and that'll be fine. If you say to yourself, I forgot to put something in before you're allowed to put it back in, I say, I wish I put this formula in or whatever, you can do it now for the final. And let's see, I have office hours during finals week, Tuesday, Wednesday, Thursday, 8:10 to 10 a.m. Use the same Zoom link. That's the 14th, 15th, and 16th. I don't have office hours on Monday during finals week because I'm giving a final. And then before you know it, we're done. Okay. So that's about that. And now I'll get started with more 11.10 stuff. And here we go. Unless anybody has a question, you can feel free to put it in the chat as we go along. But I think that's all I need to say. Yeah. Okay, so quiz Friday, exam Thursday. I will not promise I'll give you back to you the next day, but I will at least give you the solutions video so you can study off the solutions video. Okay. All right, so things that you need for 11:10, of which there's quite a bit, as we've said. Okay, on page 760 for a Maclaurin series, box 7. Maclaurin series is centered at 0. Here's a general formula. F of x is summation n equals 0 to infinity, fn of 0, x to the n over n factorial. You're basically doing the nth derivative, exponent, and factorial. 0th derivative means the function itself. First derivative, second derivative, third derivative. Okay, x to the 0, x to the 1, x to the second, x to the third. 0 factorial, 1 factorial, 2 factorial, 3 factorial. Okay. So any function which is infinitely differentiable can be written in this fashion as one of these infinite polynomials. Okay, if you're centered at x equals a, it's a little bit harder, box 6. That's called a Taylor series. A Taylor series is centered at any a. A Maclaurin series is centered specifically at 0. So it's a special kind of Taylor series. If we're centered at a, the difference is that instead of writing x to the blah, 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 it's x minus a to the blah, blah, blah. So it's x minus a to the 0, 1, 2, 3. And instead of plugging in 0, you're plugging in a. Okay, f of a, f prime of a, f double prime, and so on. Put these on your cheat sheet. Again, if you were meeting face-to-face, I'd make you memorize it. Be that as it may. Okay, and biggie that you want on your cheat sheet again is this, page 768. The first 5 are what you want to put on your cheat sheet. I've already talked about that. That's your basic geometric series. Radius of convergence is 1. We've done e to the x. We've done inverse tangent of x. I'll do sine and cosine today. You had sine and cosine on the quiz. I'll just show you a quick derivation of it. Okay. You can show by the ratio test that this one, and this one have a radius of convergence of infinity, which means it is quite possible that your calculator, when it does e to the x, sine x, cosine x, it could just do this. Right, and don't worry about these last two. There's nothing wrong with them, but I'm not emphasizing them much yet, but they're there and you can use them. Okay. And just tell you ahead of time, page 762, box 9, I'm going to give you a modified version of this, so you will need this. It's actually more for section 11, our last section. Okay, something called Taylor's inequality. That's how you can estimate a value when you do not have an alternating series. Okay, remember, we have an alternating series test and alternating series estimation theorem, okay, which says if we stop anywhere, the error is no more than the next term. You can use that for sine and cosine and inverse tangent because they're alternating. You cannot do that for e to the x though, because it's not alternating. So we have to do something else. That something else is that page that I just showed you. This thing. Okay, it's on page 762, box 9. Okay, go ahead and put it down, but I'll give you a modified version. It looks like n plus first exponent and factorial, but if you look at this, I'm going to replace this over here. So it follows the pattern of n plus first derivative exponent factorial. Okay, but we'll get to that in time. All right, so what am I going to do today? I'll show you the derivation of the Maclaurin series for sine of x. Okay, unfortunately, there's a little bit of glare coming through my window, so there's a little bit of change in shading here. Okay, so Maclaurin series for sine of x. Okay, so here's sine of x. F prime is cosine x. Double prime is negative sine x. Triple prime is negative cosine x. Fourth derivative is sine x. By the way, once you get past the third derivative, then you just write the number for the derivative. So you know how you go f prime, 1 mark, double prime, 2 marks, triple prime, 3 marks. But once we get to 4, we're not going to put prime, 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 prime. That's too much. So we just write 4, 5, 6, and so on. So here are the first 4 derivatives of sine x, and you can tell it cycles back. Then I plug in 0. So sine of 0 is 0, cosine of 0 is 1, negative sine of 0 is 0, negative cosine of 0 is negative 1, sine of 0 is 0. Okay, so plug into the Maclaurin series. But bring the book back and forth, and it's kind of heavy. So I'm plugging into here, box 7. So I'm going to go x to the 0 over 0 factorial, x to the 1 over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial. Those are already set. Okay, the only thing that changes are the derivatives. So I go 0, 1, 0, negative 1. Next one is 0. So that's gone, that's gone. So I have x to the 1 over 1 factorial minus x cubed over 3 factorial. I'm not going to write it just like that because that violates our rule of having at least 4 non-zero terms. Okay, but you can tell by the pattern, it's just going to cycle back and forth, right? It's going to keep going 0, 1, 0, negative 1, 0, 1, 0, negative 1, because the derivatives just keep cycling back. So here are the first 4 terms that are non-zero for sine. X to the 1 over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, dot, dot. And that's the way it's written in the text also. So remember, our ground rules for these homework assignments and quiz and exam, when you're writing a series out, give me at least 4 terms and then put dot, dot, dot. Okay. Now in section 11, you're asked for a particular polynomial, so you would not necessarily have to put dot, dot, dot. But when you're putting the power series, dot, dot, dot. Okay. Yes, this happens to be written as this. Okay. If you figure this out, this actually works. N equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Okay, so there it is. Let's try. If I plug in 0, that's 1. If I plug in 1, that's negative 1. Plug in 2, that's 1. So it is going to alternate, plus, minus, plus, minus. Again, notice we're starting with 0 most of the time now. X to the 2n plus 1 over 2n plus 1 factorial. If I plug in 0, I get 1. If I plug in 1, I get 3. If I plug in 2, I get 5. Okay, and you can tell that this number matches that number, so I just put the 2n plus 1 factorial. Okay, so here's a formula for the sine of x. You can prove using the ratio test that the radius of convergence is infinity, right? You can do the ratio test, put absolute value, drop that, a sub n plus 1 divided by a sub n. The radius of convergence is infinity. So your calculator could indeed do this, okay, to find the sine of any value. On the quiz I gave you last Wednesday, I had you find the sine of 1 radian, okay? And you just needed to be correct to 3 decimal places. And if you punch it in your calculator, you should get the same thing, okay? I think if to 3 decimal places, you already have, let's see, that's what? 7 factorial. No, that wasn't enough. The next one, 9 factorial is past that. 7 factorial was, I forgot, 5,040 or something like that. So that's already less than 10 to the negative 3. So you could have just added these 3 up. And if you look at these 3, it should have matched the same 3 on the calculator. So it could be when your calculator does, like on the quiz, sine of 1 radian, 0.841, whatever, right? On the quiz, you just had 0.841. Okay. Now, my calculator here, it does what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 digits. You could program the calculator or computer to say, okay, just do this until you get a term that's smaller than 10 to the minus 12 for 12 digits. And we know by the alternating series estimation theorem, if we stop anywhere, the error is no more than the next term for alternating series, which this thing is. Right? Okay, and for cosine, you can do the same thing. Or another interesting trick is to realize we already know the derivative of sine is a cosine, right? So what's the derivative of x? 1, which I can write as x to the 0 over 0 factorial, right? That's 1, that's 1. Minus, derivative of this is 3x squared divided by 3 factorial. 3 cancels a 3, you'll be left with x squared over 2 factorial. The derivative of this is 5x to the 4th over 5 factorial. 5 cancel out, and the bottom you still have 4, 3, 2, 1, x to the 4th. What's the derivative of this? Minus 7x to the 6th over 7 factorial. 7 will cancel to 7. You still have 6, 5, 4, 3, 2, 1, and there it is. So by just differentiating term by term, you get cosine of x is this, which you can write, yes, as 1. This is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus dot, dot, dot. That's how we normally write that. And a fancy way to write it is n equals 0 to infinity, negative 1 at the n, x to the 2n over 2n factorial. Again, you don't have to memorize it, but it's curious. The text also shows you that. Okay, and let's just verify. If I plug in 0, that's going to be 1, positive. Plug in 1, it's negative 1, so negative. So it's alternating. And let's see, how about the exponent and factorial? Plug in 0. You have 0 factorial, which is 1. Plug in 1, you get 2. Plug in 2, you get 4. Plug in 3, you get 6. It seems to work. By the way, some other quick checks. From trig, what's the cosine of 0? 1. So plug in 0, these are all gone, you got 1. Sine of 0 is 0. Plug in 0, these are all gone, sine of 0 is 0. Very interesting. Okay, another side note, recall from trigonometry. Okay, you don't have to write this down, but the sine of negative x is negative sine of x, which by definition means the sine function is an odd function. Very curious. These are all odds, right? Cosine, you might recall, was not odd, but it was even. Okay, cosine of negative an angle is the same as the cosine of the angle itself, which by definition means cosine is an even function. And writing it as an infinite polynomial, we get only even exponents. Okay, so hidden behind the scenes when you were taking trig, okay, well, when you were taking trig, you probably didn't see this or this, but now the cat's out of the bag, now you know. But your trig teacher may have said, oh, sine was an odd function because it had symmetry with respect to the origin. And cosine was an even function. It had symmetry with respect to the y-axis. Cosine of negative x is equal to cosine of x. Okay, hidden behind the scenes was, here's a representation for cosine. which is an even function. It's just a bunch of even exponents. And hidden behind the scenes of the sine function were only odd exponents. Okay, so that's just an extra thing, but I'm not testing you on that, but that's just a curiosity that we have there. Okay. All right, so I've gone over the derivations for each of these. Yes, we do have a formula for e to the x, but it's not alternating. So we have to do another trick to see how far we go, although there's something else you could do. So it is possible to wire your calculator for sine and cosine to do this and just have it stop. So you might say, oh, my calculator does 8 digits. Then whoever programmed your calculator, right, can use the alternating series estimation theorem and says, I'll add everything up until I get a term past, if it's 8 digits, then smaller than 10 to the negative 8, then throw that out. I will just add up all the terms up until that. And that'll be my result for sine of whatever, cosine whatever. Okay. And inverse tangent, you can do that, but not e to the x. E to the x is alternating. Okay. Now I'll say something weird. You don't have to listen to me if you don't want to. It might confuse you. You could actually do e to the negative x. If you do e to the negative x, that would become negative x. That would become negative x. So you get this to be alternating. And then how do you get e to the x? You just take the reciprocal. Right? The reciprocal of e to the negative x is e to the x. So that's one way you could do e to the x. But there's another way to do it also. The other thing I hasten to add, just for curiosity, is all of these are understood to be in radians. Now I'm guessing you and I are more comfortable with degrees. Like we like saying 30 degrees, 45 degrees, 73 degrees. We're not so comfortable with this pi over 7 stuff and whatever, right? Okay, well, the calculator is actually better in radians. Okay, in fact, so much so that, can you guess probably the way things are going if you change the mode here? Okay, so I'm in radian mode. Okay, when you're in degree mode, the calculator does a little bit more work. So let's say you want the sine of, I don't know, 63 degrees. Guess what the calculator does? It changes it to radians and then plugs it in here. Okay, no, that's the most likely scenario. So your calculator actually has to do an extra step when you have degrees, because you and I'm guessing we like degrees, right? So, oh, that's 53 degrees. That's 27 degrees. That's 49 degrees. We like that better than saying, 2 pi over 7 or whatever. But for the calculator much prefers 2 pi over 7 when you're plugging this in. So when you give the calculator something like 10 degrees, right? It's almost like the calculator says, no, I don't like that. Change it to radians and then plug it into all of these guys here, which is kind of curious. Okay, so you or I like degrees, but for plugging into the computer or calculator, it much prefers radians because it can just go directly. So if you give it, let's say, I don't know, 316 degrees, right? It immediately switches it to radians and then does the calculation after that. Okay, so just another side note for curiosity. I'm not testing you on all that, but hey, it's okay to toss in stuff that you're not going to be tested on once in a while. But now let's get started with some of the stuff here. Okay. All right, so 11.10. I'm not sure if I even showed you the homework yet. So, but if I did, that's okay, we'll do it again. So we have this funny assignment, 5 to 25, 35, 37, 53 to 63. Let me show that to you presently. Whoops. Page 771. So it's 5 through 17. I think you can read 19 there. Again, even though I have to raise it up. Sorry about that. Okay. And some more there. There's Maclaurin series. Okay. And then some more on the next page, I think. Whoops. And some more there. And I think that was it. 63, the last one. It was. Yeah. All right, so the rest of this week, I'm going to be jumping around with different problems that we have here. Okay, this is problem 11, I think. It looks like there's a 15 there. That's probably what it was in the older version. Yeah, this is 11. So find the Maclaurin series and the associated radius of convergence. Okay. Well, the radius of convergence is 1 because we know it came originally from 1 over 1 minus x. Okay, so the Melvin-Hahn ground rules are to write 4 terms. So here's the original function. Maclaurin series means you're plugging in 0. Okay, first derivative is -2. Yes, I know I didn't write the negative there. 1 minus x to negative third. Then by the chain rule times -1, that makes it a positive 2. Double prime, -6. 1 minus x to -4 times -1, which makes it a positive 6. Triple prime, -4 times 6 is -24. 1 minus x to -5, again times -1, so that makes it a positive 24. Okay, now you plug in 0 everywhere to the function, first derivative, second derivative, third derivative, and so on. So f of 0 is 1. F prime of 0, 1 to anything is 1, so you basically just have the coefficients. That's 2. Plug in 0 there, you get 6. Plug in 0 there, you get 24. These are the d's, the derivative part. Exponent and factorial are already set. So you know when it asks for the Maclaurin series, automatically you know it's going to be x to the 0 over 0 factorial, x to the 1 over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial. That's already set in stone. The e and the f part, x1 factorial. The only thing that changes are the d's, the derivatives. So 1 goes here, 2, 6, 24. Okay, that's going to be 1. 2 divided by 1 is 2. This is 6 divided by 2, which is 3. 24 divided by 3 factorial, 24 divided by 6 is 4. So 1 plus 2x plus 3x squared plus 4x cubed plus ... And this fits the rule of having at least 4 terms. Okay, so that's what we want. The thing that's very interesting, I think, is would you rather work with something messy like that, 1 over 1 minus x squared, or look at this, polynomial. I like polynomials. It's an infinite polynomial, but these are very easy to differentiate, very easy to integrate. We replace this function, which might not be so nice to deal with this thing. Okay, so that's that. Now let me show you how easy it is to do some of these other Maclaurin series. This is 7 star. Give the Maclaurin series of sine of pi x. Okay, the nice thing about this is you treat this just like any other function. Okay, so we have a rule for sine x. Right. How about right here and right here and right here, right here? Just put pi x, just like any other function. So sine x is x to the 1 over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. If you want sine of pi x to the 1 over 1 factorial minus pi x cubed over 3 factorial plus pi x to the 5th over 5 factorial minus pi x to the 7th over 7 factorial plus ... And just take it from there. (17) is very curious. And this is the actual 17. Yeah. Sinh x. Sinh by definition is e to the x minus e to negative x all over 2. Okay. Hyperbolic sign. I mean, even now you're probably saying, why do you still use the sign here? That doesn't look anything like the sign. Okay. Well, surprisingly, this looks more like the sign than you might think. and I'll show you why. Okay, first I have the power series expansion for e to the x. Temporarily ignore all the cross-offs. E to the x is x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. E to the negative x. Put negative x there, and it looks like this. Negative x to the 0 over 0 factorial, negative x to the 1 over 1 factorial, and so on. Okay. We're going to subtract this one minus this one. These two are the same, so they cancel out. These two are the same. They cancel out, don't they? This is x squared, this is x squared. We're subtracting. So that minus that, it's x minus a minus x, 2x. That minus that, x cubed minus a minus x cubed, 2x cubed over 3 factorial. Okay. Now, if I stop right here, I've only written 2 terms. Okay. That violates the rule of having at least 4, but you can tell by the pattern. Okay. This is going to be 2x to the 5th over 5 factorial, 2x to the 7th over 7 factorial. And then I just divide by 2 to get the formula for sinh. So if I divide by 2, all of these 2's just become 1s. So here's sinh x. E to the x minus e to negative x over 2, x to the 1 over 1 factorial, plus x cubed over 3 factorial, plus x to the 5th over 5 factorial, plus x to the 7th over 7 factorial, plus dot, dot, dot. Okay, so here's the formula for sinh. Problem's finished, but just compare these two. Sine and hyperbolic sine. They are exactly the same, only difference being this one is alternating, this one is not. Okay. But notice it's still x to the 1 over 1 factorial, x cubed over 3 factorial, x to the 5 over 5 factorial, x to the 7th over 7 factorial, except these are all pluses. This one goes plus, minus, plus, minus. Okay, so again, another behind the scenes, why do they call this hyperbolic sine? E to the x minus e to the negative is over 2. That seems to have nothing to do with sine x. And yet when I do the power series expansion, their Maclaurin series, they're very close. In fact, they're identical. Or if you put absolute values on all of these guys, it is this thing, strangely enough. Okay. All right, then let's see. Let me check. It looks like a 33 and a 39, depending on which version. This is R39. Okay. Find the Maclaurin series for x cosine half x squared. Now, this looks like a big mess. Okay. But if I can make it look like a polynomial, it still looks kind of messy, but it's a lot easier to do stuff with it. Okay, x cosine half x squared. So here's what you do. Started with the power series expansion for cosine. Here it is, x to the 0 over 0 factorial. Yes, I know this is 1. I like to write this just so I get the pattern. To me, once I have this, I got the rest. 2, 2, 4, 4, 6, 6, and so on. Okay, and let's see. Cosine of half x squared. Yeah, ignore this for the time being. Right there, right there, right there, right there. Erase all those x's, replace it with that. So half x squared to the 0 over 0 factorial. Half x squared over 2 factorial. Half x squared to the 4th over 4 factorial. Half x squared to the 6th over 6 factorial, and then I just cleaned it up. Okay, that's still going to be 1. What I'm trying to show here is that 2 can join down here. That's going to be 2 times 2 is 4. Times 2 is 8, so it's 1/8 x to the 4th. This is 2 to the 4th 16 times 24. That's what I'm trying to say in here. So 1 over 16 times 24 is 1 over 384. This is going to be 2 to the 6th is 64 times 720. It's this mess. 1 over 46,080 x to the 12th. That's that. And now you just multiply by x. Okay. Multiplying by x is easy. That just becomes x to the 5, 9, 13. So here's my final answer for the Maclaurin series, power series representation. Writing this as an infinite polynomial, x cosine half x squared is x minus, assuming I did this arithmetic correct, 1/8 x to the 5th plus 1 over 384 x to the 9th minus 1 over 46,080 x to the 13th power. That's the Maclaurin series for x cosine half x squared, which we don't like. It's not very nice to do stuff like that. This is better. I mean, the coefficients are weird, but at least they're polynomials, so to speak. Okay. All right, so I was going to stop there, and we got plenty of time for the rest of the week. I'll pick up from here tomorrow, so I'll stop to share and see if anybody has any questions. And if not, we're done. Check the chat. Any questions, please? All right, have a good day, and we'll see you next time. Okay, bye, everybody.